All right, so let's get started. Welcome back to Blaze Engine Stream, and today we look at getting lighting in the system. We'll see how long it goes, and we'll see how much we get done today. But at the very least, I would like to get basic one light calculation in before we do any light manager stuff. So last time we ended up finishing with a particular bug. I did continue working on it off stream to fix it, and the solution was actually rather silly. So when we transform the data in the world transforms, so that is in Blaze here. So it is scaling. Yeah, I'm back to a fine transformation, but when we were doing this with the other one, uh, the multiplications, I was doing it in the wrong order. I'm used to using column, what do you call it? Used to using right multiplications for things, while now it uses left. No, wait, the other way around. Left multiplications, while now it is right multiplications. What does that mean? Well, on OpenGL, GLM, in the shader code in DirectX and Vulkan, multiplications happen by first saying X is at a particular location, right? Sorry, you have a vector which has like X at a particular location. Then when you want to transform that location, you put a matrix to the left and you multiply by it, right? I mean, correct. So you multiply by it, and that becomes the new orientation. And you continue doing this. So if you have relative spaces, like four relative spaces, right? Like there's the origin of the world, then perhaps you have a particular uh, room in the world which is at a particular location with a specific orientation. Inside the room, if you put something, instead of using the rotation of the world, you will use rotation with respect to the room. So that's another transform. And so these are chained so that the parent is on the left. However, with DirectX math, parent is on the right. That's all. That's all we have to remember, right? In DirectX, I don't know how it works, but in Vulkan, it's on the left. OpenGL, it's on the left. In GLM, the library for OpenGL, it's on the left. So that was a bit of a confusion. That's fixed now. I also worked on getting, yes, good old STL problem. Legal solution. Still couldn't figure out I know why the problem exists. I still couldn't figure out a solution for it though. This is it. So this is the orientation test example in GLTF. It tests if all my orientations are correct or not. Initially, I had a bug. It was a pretty minor bug in loading data. I was not setting the vertex index, vertex offset, which is required right here. So this was always set to 0, and that was wrong. I had put a comment saying to do verify, and it's been done. Anyway, so continuing on, we need to get lighting. How does lighting work? It's just a set of calculations, right? So what kind of calculation? I was setting up a very primitive lighting, and I'll bring it back right now. So if you have, let's learn OpenGL because it's a very nice resource. But for basic lighting, right, they use a 0.1 as ambient. But if you're looking at direction diffuse lighting, that's lights from a particular directional source. It has two components. First is the scattered or diffused lights. Effectively, any light that comes in on a perfectly diffuse material, okay? It's also known as a perfectly Lambertian material. All the light will automatically get diffused in all directions evenly. Okay? The only difference is not evenly, but it will always get diffuse irrespective of which direction it comes in from. That's a Lambertian, right? It's not perfectly even, because if you're looking at it from perpendicular, right, from the normal, as you can see in this example, it will give you the maximum amount of light. And if you look at it tangentially, it will give you the minimum amount of light. That's a purely Lambertian surface. Real world surfaces don't exist like that. However, we will start with the pure Lambertian calculation, and then we'll slowly add other things. Okay. This is not physically based. So even though I'm talking about Lambertian is something you get from physically accurate world, like physically accurate light transport. But here we're not looking at it. Okay. Physically accurate. It's more physically based because it's not accurate, right? We don't work with spectral signatures. All of that is something we can leave aside for a second. Okay. So we just hard code it for now. First, we need the direction of the light. And we were setting this up last time, which was let light position equals minus. So we were doing directional light. So let's do that first. So directional light is light direction equals -1. This is a float 3. So -1.0 on X, that's left side. This is the right side. 1.0, that is above. -1.0, that is at the same, in the same direction as the direction we are in. Nope. That's not what it is. No. So light direction 1 means to the right. 1 on Y means upwards, and -1 on Z means towards us. Anyway, we'll see as it goes. So we already have the world normal available to us. So we can just say light factor equals dot product of light direction with light normal. So the normal. Okay. And yeah, we do need to take a negative light direction as opposed to positive. Normal is a 4. Okay. That's why I said. And we do need to normalize this. Okay, let's see how it goes, and then we can figure it out, right? Direction would be wrong right now. I haven't made the change yet. So times light factor. Times light factor. I haven't made all the required change yet, so we'll see how that turns out. Okay, the direction does seem correct. As for Y, it's because I've got it wrong. We normally use negative of light direction because the normal vector points away from the surface and light direction is approaching the surface. So the dot product of light direction and normal will always be negative. We want it to be positive because as the light direction aligns with the normal, it would be, brighter. And if it's perpendicular, it will be darker. So based on this, our particular model needs to reverse light directions. And the hard-coded light directions that I put in there are actually the reversed ones. That's why the math didn't make sense. So in reality, we would want a -1, and positive. So this is the actual light direction. So -1 means it's towards the left from the right. -1 on Y means it's towards the bottom from the top. And +1 on Z means it's from closer to us to farther to us, right? And this needs to be normalized, which again, I haven't done because it's a direction. And with that, when we take a dot product, it will be absolutely reversed. So we do need to do a negative here. Of course. dribble solution. Star. And there we go. So now it's a bit more correct. It's not actually increasing the amount of light as it was before, because it was increasing light by 70% cube root of 3, right? All right, so this is directional light. And as you can see, it's not that hard to actually implement a very basic directional light. Let's try a positional. Sorry, this is just one part of it. So we've just done diffuse. There's another part to lighting known as specular. What is specular? So let's switch from this little orientation test to a simpler model where it's going to be very visible. So I'll move to box again and we start. So you can see the box is rotating. We're very far away from it, so I should change the location of our camera. Yeah, there. So y equals 20 becomes y equals 1. Z equals 20 becomes z equals minus 2. Let's actually keep it to 2 comma 2. And so we'll face the object closer, right? Let's move the light to the other side and we'll notice a difference. We'll notice a little problem with it. So if I move the light to opposite to us, which is -1 on the z direction, -1 on y is fine, and 0 on x. So it's dead center on the x-axis. So it's right in front of us, but -1 means it will be 1 unit across the box, and -1 on y means it will be 1 unit above. So the approximate direction is that doesn't do it. Other side of that particular flat surface on top of the box. And you can see, you can only see the top side of the box now, but as you might notice, there is no glow or shine of any kind. All points on the box are equally lit. That's not how lights work in real life, because most objects are at least a little shiny. So shininess is what is known as specular lighting. So we can look at the lighting here again. And there's a section on specular. Let us say. Yeah, specular lighting. So the way specular works is it's based on how far are we from the perfect reflection angle. So if you've done your basic physics, you know the angle of incidence is equal to the angle of reflection. But in real world, we're not using perfectly mirror surfaces. We have surfaces just slightly rough, right? They're not perfectly mirror, they're not perfectly rough, they're somewhere in the middle. Based on this, the alignment of the surface microfacets. So what are microfacets? Are small parts of the surface. The alignment of these microscopic parts of the surface is generally towards the normal, but not completely. So no matter where you are, you get some amount of that surface pointing in a way such that there is a normal, like their normal forms the bisector between your viewing angle and the light angle, right? Which means there are some parts of the thing, of the surface, that act as a mirror, no matter which angle you look at from, right? If you look at from the angle of being a mirror, and if the surface is a perfect mirror, then all of it, 100% of the distribution would be concentrated at the expected angle of reflection. Otherwise, it's how far you are from the angle of reflection. We can approximate it roughly. So Okay. So, yeah, moving on, let's actually use the thing that we noted here, which is using view space. View space lighting is in fact easier, as they say, because you don't need the position of the camera. View space implicitly says that camera is at origin and it's pointing in the negative z direction in our particular uh, setup. So, sorry. Yeah. Yeah. So, with that, we can just take the world position here and replace it. Are we going to use world position at all? I don't think so. I don't think we will be using world positions, but I leave it in anyway. Float 4, view position. Yeah, position. And I should be able to get it from the other side as well. Ooh, my world position has been wrong all this time. It's like this. Clearly, I'm not using it because if I was, I would be having a bug. I'm going to remove world position completely for now. I'll change it to view position. That's fine. World position is gone. If I need it at some other time, I will bring it back, right? Right now, I don't need it. View position. View position. Okay. Cool. So now, once we have the view position, it's in view space, which means what I'm seeing is exactly the difference between us to the object. So any position is the same as the direction when you normalize it. And with that, I just need the angle of, so with this, I just need the angle of the normal with the light, right? So as you can see, what they're doing is taking normal view position minus frac pos. We don't have to do that because we already have the view direction. It's just the normalized view position and the reflected light direction from normal. So we have the light direction here. We need to reflect it. I will change this soon, but reflect light direction across the normal vector, which is world normal. Okay. So this has to be again xxx. Sorry, xyz. So that reflects it. That gives us what we want on the refill here. It will have to be dot product, as you can see, with the viewing direction, which is just view pos, but let's make it specific. So view direction equals normalize view position. Okay. REFL is reflect vector or I think it's fine. Call it reflection vector, right? Finally, specular equals power max to the power of 32. So it's dot of the reflection vector with the view direction to the max of this thing, comma, as you can see, it's 0, 0, because we don't want it to go below 0. And finally, you power it up to 32. Why? Don't ask me. I will read about it soon enough. But mostly it's got to do with how bright it is, as you can see here. And they're not doing physically accurate, so you just say what is the specular term here and you can use it as you like. Right? So light factor becomes diffuse factor. We don't have light colors, so these are simply just factors, so to speak. So this is diffuse factor plus specular factor. Diffuse factor plus specular factor. And we are assuming we're making a very small assumption here, which is actually, I don't know if it's a very small assumption, but we're making an assumption here that diffuse plus specular both have like the 1.1.1 color, right? The light is 1.1.1, and then it's not attenuating at all. Yeah, of course, we just change the shader so it won't be a star. Okay, we can't see anything yet either. Perhaps because we're not in the right place for it. The thing is, light position is set to -1, comma -1, but the flat surface is actually at 0.5 height because the box goes from. I'm not certain actually. Is the box from -1 to 1 or is it from 0 to 1? So let's switch this to -2. Oh, actually, it is facing downwards, so it is -2. Yes, we do the right direction here. And Z is -1. Let's make it. Let's keep it -1. So if the flat surface is at a height of 1, and we're looking at it from -2 height, we're looking down -1 height. We're looking forward 2. So this thing needs to be at Z equals 2 from that position, and Y equals, yes, it's literally the reflection of us. If we are at 2 comma 2, then this needs to be at, oh, it's going to give me an okay. Well, that doesn't seem to have worked. So let's tweak the camera position a little. Let's make Y equals 1 and see. Okay, as you can see, Y equals 1 is still a little above it, so it's at 0.5. And if that's the case, this would be a better result. We'll see. Star. You can see there's a little glint passing across the bottom. It's entirely a bug. I did something wrong here. So view direction, reflection vector takes the light direction and reflects it. Minus of a light did. Yeah, shader. I'm not certain I'm seeing anything actually. Let's move the light to the right hand side. See if that changes anything. So Y equals 0, X equals 2. Start again. Since Y equals 0, since the object is in motion, yeah, now we can see a little bit of that specular happening. The question is the directions correct? So what did I say light is at? Light is at 2. Direction of the light is +2, which means light is arriving from negative 2 to 0. So now we move it to right hand side. Where we move it to left. That seems to be working all right. Since it is behind, since the light is behind the thing, it doesn't reflect for a long time. So I will instead make it to the right hand side, precisely to the right hand side. And now you can see the little shine passing through the surface. Okay. So diffuse and specular don't actually just add up like I have done. Normally, diffuse and specular will be multiplied by the material, which has metallic and roughness here, but generally it would use other physics parameters for this. In this case, we just take the roughness and we apply it here. So this is roughness. What's material under? For instance, data, which is in PCB. So it's under PCB. PCB dot roughness. So diffuse factor is times roughness. And specular factor is 1.0 minus roughness. Okay. Of course. Oh, we build and run. And that is expected. So the material actually has a roughness equals exactly 1, if I remember correctly. No, roughness should be 1 actually. The calculation has some issues. Let's check with render doc, shall we? Launch application. Was it? I know we can't see anything, but that doesn't matter. We should be able to just check Python state, fs, push constants. Roughness is 0. Yeah, then it makes sense. If roughness is exactly 0, then specular will be the only thing we can see. And so this is actually correct. And we are loading this from the material. So that is just fine for us. All right. Moving on. So that's specular and roughness. We can set this specific thing up. So instead of directional light, they're using point light. So let's set up point light. So we'll just do position now. So this is directional light here. Instead, we'll do position. So light direction equals, so nope, let light position equals, now we can just place it, float 3. Let's place it at x equals 2, y equals 0, z equals 0. And the direction of the light will be based on the particular position of this. And now we need world position because the light position is not, light position is in the space of the vertex. Sorry, the world. It's in the world space. We can do 2 things. One is we can just use the view space as we have it, and light position can be then rotated into the view space, which is a valid and possible thing to do. We will just have to use the light position in the vertex and then pass it in. Problem is, if the number of light increases, the calculations will keep increasing. The alternate idea is to do the calculation in the view space again, in the world space again, right? So float 4, we take world space, so world position world position. We get the world position here. World position goes from vertex out to, so we copy this. Oh, view position has been wrong all this time. Let's check with the correct view position, shall we? So we undo all of that. We leave that in. View position should not have projection in it. So it's just the view and the world transform. So build, start, first, rebuild, start. Okay, that's actually a bit better. Let's see if we can get the 128th thing that they showed. It's a much sharper image. You can see the image is also much sharper on this now. All right, let's keep it to 32, the power, and let's get some data to this. So we need to now know where the camera is. For this, we need to pass in the camera position in camera data. Camera data is in the miscellaneous data struct here. We have camera position already available to us. All we need to do is move it into the camera data right after the matrices, because matrix has higher alignment requirements. Actually, it doesn't have higher alignment requirements, but it's always better to put matrices in front of vectors, just in case. Anyway, that will bug out on this side because there we go, right there. Hi there. And this again becomes camera data dot camera position. So that gets us camera data into the shader, which is here. So float 4 position. And now that we have camera position, we can just use it. So we no longer need view position. We can go back to world position. Lower position. All right, so we can use world position here. Right there. So continuing on, put it connected here as well. Okay, so now view position is no longer just world position. It's also minus PCP dot. No, it's not PCP. It's camera. Camera data is in a parameter block rectangle. So it's camera dot position. So now that gives us the actual view direction. So I said, does it matter where I'm from? I don't think so. So let light position equals so we're just saying there's a light position. I will say it's at plus 2.0, x-axis, y-axis is 0, z-axis is 0. And now light direction becomes light position minus world position. Right? So that's actually the direction that the light is in. What we want is actually the other way around. Just we're looking at the direction the light will arrive at the world position. Okay, so now just by doing this much, effectively we've ensured that each pixel on the surface of the mesh will have its own light direction, which will be different because we're using point lights. And it doesn't change all that much here, since it's just purely Uh, it has no specular, but let's actually say roughness equals 0.5, right? So in that event, I can remove this, remove that, and set this up with a 0.5. With that, I can do a build and start. And now you can see like there's the light and there's the specular shine just going past it. Okay, moving on. So that gives us the basic light calculations. I call them very basic because they're not physically accurate or anything. They're a decent approximation for what was used in, let's say, PlayStation 2 era of graphics. But most modern lighting systems do not use this, right? Now, from there, we need to find a way to get this data to the shader. One way is to just add another block like this that contains the light data. Just like camera data, it's a per frame information. So with respect to that, we can just add it not inside camera data, but a second struct or light data. This, however, puts a limit on the number of lights. I'm not very happy with that idea. So instead, what I will be doing is I'll say light data, which will be arrays of lights, right? What kind of lights? Well, there are two kinds of lights. So struct point light, which has a position. So float for position. Hey, Sumela, it has a color. So float for color. And what we can do is we can switch it to float 3 and we can use the wasted space for other details such as range and attenuation. Didn't think I want to put attenuation here. Instead, intensity might be better. But I think the float 3 can handle intensity alongside the color. So it's normally two things, which is range and light. Let's just make it attenuation. Okay, so that's point light. That's one piece of data. Second is directional light. So directional light. Directional light contains direction, intensity. Again, didn't we just say that we don't need intensity? We're just padding right now. Color, which you do need. And again, directional lights don't have attenuation because they don't have a position in the world. They simply have a direction. And that seems to be it for now, right? For the directional light. However, I will pad it because it's easier to use with padding. That way we don't have to explicitly keep into account what is happening here. And the light data becomes nothing but a pointer of point lights with a count and a pointer of directional lights with a count. And so the counts are event, point, light, count, event, div, light, count. Right? Simple way of doing things here. And we can say something like get point light, right? So point light, get point light. Oops. We can then index it. So uint idx, and it should return the point lights, idx. We need to ensure that this is always inside indexes, because on GPUs, out of index bound can literally crash the GPU. That's a price we pay for using structures like pointers in GPUs, let's say. So with that, I will have to manually say if point lights. Oh, sorry, I wasn't watching the chat. After your video, I suppose, let's see what it does before we decide, before I see anything. If point light count is less than IDX, but if IDX is greater than or equal to point light count, that makes more sense to me. We return point lights 0. So this means we have to guarantee that point light 0 exists. Otherwise, it will return the correct one, so that is fine. We need to do the same thing for directional lights, so we just paste it there. Get directional lights, directional lights, directional light count, and again, dead lights, right? That gives us directional lights from here. So we get both point lights and directional lights. We should be able to use them out here. So we'll come to that in a second. Right now, we have none of this data that is set up, right? There's no place where we're actually sending it to the system either. So inside parameter block here, instead of putting just camera data, I will say struct frame data, where per frame data is camera data. Camera plus. No, it's a yes. The question is, how do you send it to me? So I was thinking I'll see the video first that you make, and then decide if I find it interesting enough. Your data, light data, we get lights. Okay, so camera data and light data, that comes in there. This becomes per frame data instead. We'll call it PFD, which is definitely not a good thing to do. It's not a good naming scheme at all. But it is what it is. Yeah, that's the thing. I don't want to give that publicly. PFD or Emerald household. Hold on, this was not a part of camera at all. You should be if household. Okay. So based on this, we've got the basic stuff done. I can just take this part and do a little bit of optimization for the future, which is float 4 is float equals that, and this is nothing but void position here. That's void position there. Okay. For the rest, you just trust the compiler to optimize it away for you. But otherwise, this is what we want. That might be nicer. Oh, okay. Now we have light data available to us here, possibly. I say possibly because it doesn't actually exist until we can, you know, use it. Okay, hold on. Another one here. pft.camera. All right. Build solution that looked fine to me. Miscellaneous data. It just has camera data here, right? So what I'll do is I'll make another struct for light data later. Right now, I'm going to use that to pause compilation. Start. Okay. It still is working, even though we haven't sent any data on it. So light data. Then we construct a struct called light data, which contains what it needs is a pointer first, two sets of pointers. So I'll put a comment here saying pointer to light to point lights, pointer to dim lights. Why am I saying a question mark? Because we don't have any way of getting pointers right now. There's no way of having pointers that we can send to the GPU that we have used so far. That is a key point. That is just a matter of things we haven't used yet, not things we don't have. Okay. So how do we get that? Those pointers. First of all, best thing to do would be to create a buffer. What kind of a buffer will this be? It's not a vertex buffer. It's not a uniform buffer. We have ways of creating those. Instead, this one is what is known as a storage buffer. So we'll go to the render device, not render device, actually buffer manager. And here we create vertex, creating next buffer. We will create the storage buffer as well. So create storage buffer. All right. With that, we need to generate a definition. So let's do that. Copy all of this, which is for the index buffer. So we just copy all of that down here into the storage buffer. Now you might notice that there's a lot of repetition of code happening. At some point, this can be optimized. It should be optimized. Right now, don't care. So we use a storage buffer bit. That's it. That's the only difference. So are you not going to make it open source? That's the first question. If you are, then you can just send like the GitHub. So here, I can say we can. Yeah, I have to. I normally use that quite a bit. GitHub is, I just open source things. So it's always there visible on GitHub. The only reason the code for this project is not on GitHub is, well, I don't know why it's not on GitHub. It's just because I was lazy to set it up, I guess. It's on another Git site of my own, but not on GitHub itself. So so what we want right now is device address. So you see this thing, but it's a buffer device address. Buffer usage, shared device address bit. So that's what we want. That's in here in the usage. Okay, buffer device. Buffer usage shader device address bit. That seems about right. Okay, so buffer usage shader device address bit is done. This should give us a pointer that is available. That is something we can fetch we will have to somehow fetch it, which means buffer manager suddenly has a new function. Of course, fetching it can be a little troublesome. So instead of manually fetching it every time, we will add it out here. So here it is UN64T and buffer address. Okay? Or device address, I suppose. Cool. So device address, once I have device address, what do I have to do? So I need to add it in the creations. So down here, when you create it, my bad. When you create it, device address can be directly gotten from the allocation info. As you can see, there is no device address actually. Ha, my bad. Set it down at somewhere. Not on stream. 1 second. I'll do it on my phone. Got it. I got it. I'll check it later. It's downloaded. So device address has to be manually added then. So how do we get that? That is wiki buffer. We can get buffer device address right there. Device, which comes from in the device.device. The info, which is buffer device address info. So device address info. We get buffer device address info. First device address info equals that dot do all of that so we can structure type buffer device address info. The XML pointer buffer is index buffer. I need to change the name there because this is actually the well, this is actually the storage buffer. So this just directly returns the buffer device address, right? And that's its own type. So I don't actually need to do all of this. I can just say it's VK device address as the type. So go there and change this type to VK device address. There we go. Okay. Now, one other little thing, which is this is in fact create index buffer. So I have put my code in the wrong place. Not necessarily, because we might just want the index buffer to have direct device address at some point. But right now, let's be correct. So this is the storage buffer version. Device address info is still left in there. So copy, paste it here. And now we can change things in here. So storage buffer create info, allocation info, this becomes storage buffer, allocation. The storage buffers were initially added in OpenGL as a way to get like larger memory data that wasn't using all of those faster memory locations from uniforms. Right? Uniform buffers are relatively faster, but they're also more limited. So this was added. But now, if you take an AMD device or consoles, storage buffers are pretty fast, right? NVIDIA still has uniform buffers faster than storage buffers, but on AMD, it's almost faster to use. Not faster, but like almost as fast to use storage buffers. And it's, um, you might as well just use that for convenience. Anyway, so now we've created this solution again. That's storage buffer. It's done. Cool. Storage buffers have device address. Nothing else does. Device address has to be set properly. So I will ensure that this is initialized to 0 on the others. So device address equals 0. And vertex buffer dot device address equals 0 as well. Okay. So that's device address for us. Plain data carriers. We don't particularly care if it's valid or not because this data is never seen by anything outside of buffer manager. So buffer manager itself, right here, it does a fetch buffer. This will be deprecated eventually, but for now, it's fine. However, device address will never change. So we get device address, fetch device address for a buffer ID. And on the other side, this doesn't need to be fetch, but anyway. So if this whole thing here, not invalid and all of that, I went back to the old Zoom. Okay, that's better. If not invalid, then return this thing. Okay, if not is valid. Next, so you fetch the buffer first. We fetch that data. So buffer equals, we fetch it. Then if buffer dot device address, if buffer dot device address equals 0, return std null again. So we don't return anything if address is 0 because we don't have an address. Finally, if all of that is fine, then we just return the address. And that's the end of it. Okay. So with that, we can fetch the device address on the main side. Now in the miss data, out here, if you go to where camera data is, you have the light data. It will be easy enough for us to create the light pointers. So we can then say light buffer, which is buffer ID, buffer manager. Do we actually not have a single buffer manager here? That is very interesting. Buffer ID, sorry. That is interesting that we don't have any buffer IDs here. So first buffer ID will belong to directional lights, point lights, night lights. Second one can belong to directional lights. Do we actually need two buffers? No. Is it going to reduce the amount of headaches I have to deal with right now? Yes. And that's it, right? So coming back after device, descript the pool, then the uniform buffer, then we destroy these things. So first render device dot buffer manager destroy free buffer and give it the buffer IDs. So what's the first buffer ID? It is point lights. Second buffer ID is directional lights. None of these actually will work without a move. So add std move, add std move. All right. Now that frees the buffer. We haven't created it yet, so That is something we need to add now. We, where is it? So, okay, we're doing an init here. This is raw data of some kind. So all of that is the pipeline code. This is the camera buffer creation. And beyond this is the descriptors. So this is the right place to put lights. Okay. First, we want to create the light buffer. So that's the point light buffer, sorry. Point lights equals, now we get the buffer. So that is created from render device dot buffer manager create storage buffer. We need the size. How much should the size be? So it should be point light, size of point light multiplied by, let's say we can have 10 lights. Yeah, I know, just 10, but those are 10. Now, point light is not a struct on the CPU side. So what I will do is I'll just copy it from the GPU. So that's point light right there. I'll also copy the directional light while I'm at it. In this data.h, above light data, I'll say point light and directional light. Okay. Now, these need to be settled. So this is not actually a pointer. So this becomes vk device address, point lights, and vk device address, directional lights. Okay. And with these two, we should be able to pass all the data we want. We just need to assign the point lights correctly. And here, point light has a float 3, which is nothing but DirectX XL float 3. And same for directional light here. Okay, so that's point lights, direction, color. One thing we can do is, since the number of lights is generally small, we can actually convert the lights in view space on the CPU before we actually send it to the GPU. Perfectly fine thing to do, not something I'm going to work on right now. So with this, we have the structs here, we have the light data here. We haven't set it yet. So inside init, right there, we try to create a storage buffer worth 10. This, if it doesn't work, we have to do something. So auto lights value equals this. If point lights value, not point lights value, return false, then otherwise, if it's a valid point lights value, then we can extract the information. So we can say point lights value, the value. So point lights equals point lights value dot value. Okay, that sets point lights for us. This has to be moved. RS to be moved. There we go. We copy and we just paste it again. The second set of things becomes their lights. Their lights value 10 times the size of directional light, which is actually the same as point light for now. Their lights value. Their lights value. Okay. This also becomes their lights. Okay, directional light. Fine. So with this, both of these buffers are complete. Nothing's been written to them. That is fine for now. What else do we need? We need to assign their buffer data to light data. So light data dot directional lights equals render device buffer manager, fetch device address for directional lights. Yeah. Dot. And here I'll just say value, right? It has to be correct. There's no way this is false. So I will just say value. If it is wrong, if there is no device address, then the program will crash. And that is acceptable because there's something wrong with my programming for this to happen. All right. Now with point lights and directional light sets, we will have actual pointers on the other side. We just need to write lights into point lights and directional lights. I will, for the measure, also say lights dot get light count equals 0 and lights dot point light count equals 0. Okay. Oh, all right. So now we need to find a way to write to these. Luckily, missed data is just random data. So we can write to these on the fly if we want. For now, I'll hard code it in the beginning of Blaze here. So out there, when we load, after we load entities, I'll say, actually, I won't say anything. Let's start with 0. Let's start with 0 and then we'll move forward from there. So mesh.slang. Now here we get the point light. You get all of this. Light data is currently not written to the uniform buffer, so that needs to be corrected and quickly at that. So frame data is camera in light data. We haven't written that, so good time to fix it before we forget. So we get to the right uniform buffer here. Descriptor buffer info as camera uniform buffer. Size of camera data, which is not good enough. Not good enough at all. So size is just size of camera data when it should be plus size of light data now. Plus size of light data. Okay. That's it. This should work out by itself. All of that should work by itself. This here should take camera uniform buffer size instead of the calculation, so it will be forever correct. And now the uniform buffer has been written to, and it has an approximately correct size. So I'll run it from the render doc. That way we can see the issue. Hey, some issue. Abort. Hey, what happened? Doesn't show anything. I started here. Is abort. Buffer device address is not valid if VMA allocator create buffer device address was not used. VMA needs us to actually tell it that we will be using buffer device address eventually. So in the render device CPP, VMA create allocator right there. Is it here? I think it was allocation, not allocator. So buffer manager, create storage buffer. I can run it again. VMA allocator, create buffer device address. Okay, it is the allocator. So it is in fact in render device. VMA allocator, create allocator somewhere down there. Allocator create info. So here flags require this one. All right. Let's try it now. It will probably ask for a feature. It did not. Okay, good for us. We can run it in rendered off now. So last settings, launch. Let's see. One captured. Yeah, where is it? All right, here. We go to mesh viewer. We not mesh. We leave this one. Vertex shader has PFD, per frame data. So per frame data tells us light data and camera data. Both are available. Light data has these two matrices in the position, -2 or Z. -2 or Z for the camera, yes. All right, light data. So point lights is null, tail lights is null, and the counts are 0 and 0. This null here is wrong. In the sense, it shouldn't be null. It is null because it's only writing 0. Because even though we copied the uniform buffer, so we created the space for the uniform buffer, we never wrote to it. Disk data, back we go. Where is it? The description, that is fine. There's a write somewhere here. Hello? Yeah, it'll be more like mem copy. There it is. So uniform buffer is allocated and we already mem copy the uniform buffer data. We don't have the lights available to the uniform buffer. And because of that, there's a tiny little issue. I finished the lights there. So copy the lights there, finish the camera. And then this becomes uniform buffer, which is a separate block from the others. Okay. This takes the right data. This is fine. Then copy all that. Map data, this thing. From buffer pointer equals allocation data, map data. Okay. And I'll take this. I'll say map data, which is void pointer. So I need to offset into it, which we have from here. So I should be able to use that directly. Camera, uniform buffer pointer. I'll move this above. And I'll swap that as well. A good measure. Instead of taking camera data, it will now take the lights data. So the size of light data as well. And here it will add size of camera data because we need it offset. Build, rebuild solution. We will run it on this side. Okay, captured one frame, that's enough for us. Pipeline state. Vertex shader, PFD has light data here. And there we go. It does say a buffer. So there is a buffer created, 148, and it says +0. That means offset 0 in that buffer. We are free to just use the same buffer with both of the data written into it at different location. In fact, that is the ideal way of doing things. However, for now, we will just leave it as two different buffers. We're not going to use this forever, right? And so you can see the data here. It's zeros everywhere. And now, out here, we can write to it. So list data, upstate.list data, pointer, light data, and load point light count equals 1. Point lights cannot be written into. Instead, again, abstract.list data, point lights, which is a buffer ID, app state, then the device, buffer manager, write to buffer ID. Ooh, really, that's a lot. Point light, so we create a point light, and this is not available this. This is actually misc data point light for now. Point light dot. So we have color, which I will temporarily set to Position equals -2 on the x-axis, 1 on the y-axis, 0 on the z-axis. Range equals 12. Attenuation equals 1.0. I'm not using attenuation yet, but I'm writing it anyway, just in case. And with that, I should be able to just say point light, come on, let's spare. Okay. With that, it has been written to the buffer. It should be usable. Should be usable just fine. Start. Buffer size 32. It can't write to that buffer. The size is 32, which is greater than. Ah. That's a funny one. So we need to do this in the reverse. We need to assert that size is less than or equal to buffer. So far, it's been equal to, so it just worked. Okay. So that's the original behavior. That is just behaving as it was with the hard-coded data. This one. Now what we will do is we will add this manually. So we'll say flow 3 diffuse. Okay. As you can notice, it's flow 3 directly equals 0.0x. And we do that for specular. All right. Then for, I think this for I should be able to use for int int r equals 0 or I less than or I not equal to. It should be roughly the same, but let's do it. Less than this light data, which is in PFD. So PFD dot light data dot point lights. I'm not going to do dead lights right now. It's like count plus I. Okay. In here, I will just do PFD dot light data dot get point light. All right. That gives us a point light. Okay. Now with that, hold on, what's happening to this? Here we get the point light by data. So light position becomes point light dot position. So point light dot position. Light direction works out. Diffuse factor gets calculated through this, where it's actually just a factor. Now diffuse plus equals point light dot color multiplied by diffuse color. So diffuse factor. That's how much diffuse is affected by this particular light. Similarly, we now need to do specular. So we say light view direction, reflection vector, which takes a light direction, specular factor, which I think should just work based on how we've written it. Specular equals point light color times specular factor. Okay. In this particular model, specular light should have a different color than diffuse. Diffuse light and specular light should have different colors because we're not using PBR. But I particularly do not care. We will move to PBR very soon. So Yeah, diffuse plus specular. Okay. And this for the same. So diffuse factor, we remove the factor. Specular factor, we remove the factor, right? The issue is this is a float 3. We expect a float 4. So we multiply this by a float 4 of this thing, comma 0.0f. Cool. And this is the same thing here, so we'll just copy and paste it. Great. Build, because this was a pure shader build, we have to do this again. And restart. We see nothing. That's not right. So we can check what's up. So this is the old round. Run this again. Close. We go back here. And if we go in there, light data was not updated at all. Why not? Did we not write? This is CPP. Did we not write? Write to buffer, point lights. We wrote a point light with size of 1. We did say light data or point light count equals 1. So what did we do wrong? Yes. The pointer. So light data here doesn't belong to the same buffer, which is point light count was still 0. If we go and look at point lights, you'll see that the first one actually has all the data. So we did write the data, but we did not write the point light count. So for that, we will have to write to that buffer, which is a bit of a pain, or would have been. However, luckily, we have a camera uniform buffer pointer, so we can write to it directly. Mem copy, uniform buffer pointer plus size of use data, camera data, comma, there goes the light data. So that's app state, list data, light data. That's it. Comma size, which is size of app state, list data, light data. Okay. Now let's try it. Hopefully we'll see a light. We don't. Don't see a light. Launch, load settings, launch, don't save. Close that. Back there. Pipeline state, vertex shader. Let me select the right state. Vertex shader has a buffer 152 here, which contains light data. Point light count is in fact 1, which does have this point light. It should be working. So what's wrong with the shader then? Diffuse is added, specular is added, color times diffuse factor. This part is the same as it used to be, same as it always has been. So what went wrong? So diffuse and specular, are we multiplying, huh? Or is it addition properly? It is in fact addition, as it should be. Let's add a 0.3 as a factor in here for a bit of ambient light. Start it. Of course, we know this problem. The build solution. Now we run it. So we can only see the diffuse lighting, nothing else. Okay, instead of any of these colors, if there is a light, we will just add 1.0 for diffuse and 1.0 for specular at the very existence of a light. I'll remove the 0.3s And okay, so there is light. It does know there is a point light. That's not the problem there. It is very well aware that the point lights do exist. So the problem here is mostly in getting the point light. That's one possible problem. The other is the diffuse factor. So let's see which one. Point lights, and you index it, and that's fine. So what could be wrong? Sound like count is one. Start was set to one. That's why this assignment, this addition worked last time. Possibilities are place the light in the wrong direction. So let's see. Light is positioned at minus 2x. X equals minus 2. Y equals 1. So it's 1 unit above, 2 units to the left. Blaze.cpp, I shall change the positions. So instead, I'd say the position X is at 2, Y is at 0. So that's the same level as us. This is a purely reflective surface. So we need to be careful with this. That thing works with X equals 2, Y equals 0, Z equals 0. Okay, so what's happening with it? Build, will solution, start. So this is it. Like it has nothing in it. You can see in the depth, it is drawing. All of that is just fine. So what's happening? Definitely something to do with this, but what? So we do know point light dot color. Similarly for specular. Early with the given roughness, it would be purely specular, but we'll look at it. We start. What are the light colors? It is 111. So point light dot color is 111, right? So it should increase the value by 111 if it even goes through here once. The fact that it's not is telling me something. Meanwhile, if I set this exactly to 1 and I run it, then it did collect. Sorry, it did light up the scene. Yeah. It is going inside the loop. It's making at least one loop. All I can see here is point light that is being asked for is not indexed properly. So let's just say dot point lights and then I manually index it, right? You'll see then if it's correct or not. Ah, it's at build. Start. Okay. So effectively it seems like the fetching data through that getter doesn't seem to be working so well. We'll eventually have to fix the getter, but for now, we'll keep moving. Start. There we go. We have lights. And these are lights that the CPU can tell us that exist or not. And to be fair, we can just load multiple models if required to test how this looks. So let's swap models. We can do this all on CPU. So instead of box, let's go back to using orientation test.glb. So that's the orientation. Now, point light is fine. Perhaps this should be a bit further away. Or we can start. So if we start it, yeah, we're still inside it. That's not good. So I had to go outside. For that, camera needs to change location. Initially, it was set to 20 because that's roughly how big that cube is. Not roughly, but like it's smaller than this. There we go. The light itself is also, I think, inside because I think it's 5x5, probably. So, what 10, 7x7 or something. So I put the light at 10 on X. There we go, right? So it's pointing from this location on the right hand side. What I'll do is I'll add another light, this one at the top. So second light, point light, make it an array. So std PMR vector, make it a vector, why not? Yeah, I can go manage. It's good enough. Array of size 2 takes 2 of these. It was over here. Well, now we're here. And this data point light can be moved over this data point light and the second data point light right there. So with that, I can remove the array template specifiers. Cool. So this one should be at y equals 10. 0, y equals 10. And here, instead of doing all of that, I can just give it a point light, right? Still, oh wow. That's no good. At that point, might as well not use the span, you know? Okay, the second light is not being used because I'm manually doing all of this, which means point light count has to be manually added. But what I'll do is I'll point light dot size and it counts. There we go. Now we start it. Oops. Now we have a light from the top and the light from the side. The side one doesn't appear so easily, but the top one does. Instead of 10, perhaps we should set it slightly larger. 12. 12. And similarly, perhaps the position of this one shouldn't just be, sorry, not that. The X one shouldn't just be X-axis, but also Z-axis. Start. Or it should be minus Z. To be closer to us, effectively. So we see it more often, the light. And now you see it. You can see it sort of bleed off quite fast. That's because it's a specular. Specular lighting doesn't always color everything, that's it. Cool. So with this, we have some sort of a lighting on here. It may not be physically accurate. It may not even be completely let's say, good looking or like properly implemented, but it is some semblance of light. The reason I'm not going to go further into lights and just use this is because we will be moving to physics based rendering, PBR, and then we will be re implementing lights anyway. So, right now, the point is to get data to the GPU. And the next thing I will do is actually make it more efficient to get things to the GPU, right? Currently, we're just writing manually to the buffers. All of that needs to be a little automated compared to where we are. But that's it. Thanks for joining. I hope you enjoyed. See you next time.